Alright, so this is the last video, all dealing with the Gibbs factor. Again, we're going to continue doing a few practice questions. Now, this is the next question that we're going to work on, but I want to point out that the way I'm about to show it is going to use some slightly different variable terms that we'll come up with in a second. But for the most part, it's just going to look a little bit different from what you get. All right, so the question is, what's the probability that one and only one oxygen molecule, or yeah, oxygen molecule is absorbed on a hemoglobin molecule, and then probability that four and only four are absorbed. So pause the video, work on this stuff, and we'll go over in a second. All right, so they tell us here that a molecule can bind up to four molecules, that there's an energy E for each bound oxygen molecule. Um, and I think that's pretty much all you need to know. So this is what's going to be a little bit different. So I'm going to take the Grand's Gibbs sum, but I'm changing up the way it's written real quick. So the way we're going to write it, just to make it a little bit nicer, because they don't technically mention mu, so technically we shouldn't have it in there. So instead of having e to the n mu minus epsilon, what I'm doing is I'm splitting this that exponent up into an e to the n mu times e to the negative epsilon over tau, and then I'm just replacing e to the mu with lambda. Like I said, this is something that I'll show you in a bit. But our grand partition function is going to look something like this now. Now, what we want to do is try to come up with a way of figuring out what it's going to be for all the particles. So for one bound hemoglobin, it would end up looking something like this. This would be whether it's not bound, and then this is it's bound. So this is what it looks like. And then we also know for 4, it would look something like this. Again, pretty much the same thing for all 4. We can almost treat each site, they say here that each site is independent. So you could say that this would be for site 1, and then times it by for site 2, times by site 3, yada, yada, yada. So this actually expands into looking something that looks like this. 1 plus 4, blah, 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 blah. So that means the probability of it occurring of one molecule being absorbed would be equal to this. Now, the way we actually came up with this, well, one way of realizing is that this equation, when expanded out, basically tells us everything. This first term would represent, because remember, the grand sum partition function is a combination of all the Gibbs sums for every single Gibbs factors for each different state. So this first term is referring to the possible states for no oxygen molecule absorbed. This would be for one oxygen molecule absorbed. Then the next one would be for 2, and then for 3, and then this would be for 4 molecules absorbed. And we can actually see it here that this does match with what we would expect. Here, the value of n is 1, and the value of epsilon is just e, which is what we would expect for one bound molecule with a total energy of epsilon right here. But because there's 4 different sites, that would occur 4 times. But for this last one, for this would be for 4 molecules. 4 molecules are being bound, and the total energy would be 4 times epsilon. And this can only occur once because there's only one combination that will get you 4 of them. So this allows us to actually make the probability a little bit easier by expanding the equation out. But again, we could have just done this, this is just a shortcut way of seeing this. But yeah, the probability will end up looking like this. This term for one bound oxygen state divided by the total number of states. And then part B, again, pretty much do the same trick, that this is for four molecules being absorbed, and then this is the total. Of course, if they asked us something else like up to four, then we'd have to fool around with these equations. But I mean, clearly, if it's the probability up to four, it would just be one. Now, the only difference between what I have and what you would have had is instead of this lambda, you would have had a mu minus epsilon in front of these terms. So I just wanted to throw that out there, that the equation still would have worked out the same way. It just would have looked a little bit different on your part. All right. So the Gibbs factor. So once again, now that we have, just like we've done with the Boltzmann factor, remember the moment we found a probability, we can immediately find average values, because average values, remember, are set up as a sum of the weighted parts. So we can do that here. Say that the average of any variable is the variable times the probability of it occurring, and we know that the probability of it occurring can be represented with, or substituted with, the Gibbs factor divided by the grand sum. If we want to find the average number of particles, we would replace that with n. And of course, what we can do now is see the relationship between this and n, and rewrite this so that it looks a little bit different. So for example, if we looked at the partition, or the grand partition function, and we took the derivative of this with respect to mu, what we'd end up getting is this. The minus epsilon s drops out, so it would essentially just be n tau times e to all this garbage. So if we pull out a 1 over tau, we actually can see right off the bat that we get whatever we had up here in the numerator. So from here, we can say that the average number of molecules is equal to this: 1 over the partition function times this partial derivative, just like we got it last time. And then once again, we can actually combine this 1 over the partition function into this partial derivative by turning that z into ln of z. And then this is actually the thing that I was telling you about how we can combine we can replace that e to the mu over tau with a lambda. And this lambda is actually going to be defined as the absolute activity. So it's just a way of kind of trying to neaten up the equation a bit. So here you go, like that. That's really all it does. So we can actually go back to here and fool around with this a bit and rework it so that it's actually now in terms of this absolute activity rather than in terms of tau and mu. So again, whichever one fits whatever you're trying to do. And then, of course, we could always find the average energy like we always do. And we do this. Another shorthand that you're seeing me do right now is I'm including a beta as 1 over tau. This is actually, again, something that you can see in some of the other books or on other sources. Instead of using tau, they use beta. Just like last time, we can kind of fool around with this a bit. So one thing that we could do is change our definition a little bit to look something like this. That the total internal energy is the average of this value. Separate it to look like this. And then plugging in that it's going to be equal to all this stuff. Again, a lot of the same stuff that we've done before, moving things around, trying to simplify, change different variables and things like that. So we can look at an example with the Gibbs factor. So here we can consider this single myoglobin system that could either be vacant or have zero energy. can be vacant with zero energy, or occupied with an energy of epsilon by absorbing an oxygen molecule. And as we know, the Gibbs sum will look something like this. It could either be vacant with no energy, or occupied with one energy. So then when they're in equilibrium, what we could say is this, that the mu values are going to be equal, which means that the activities are going to be equal. Um, that activity actually, if you go back to what the whole equation was for mu, and the whole e to the mu over tau, uh, what it turns out is that the this lambda term will actually simplify to look something like this: n over nq, or p over tau divided by nq. So again, another reason why we kind of, it makes it nicer to work with this lambda term is because it's very easy to figure out what the lambda term is. It is actually a very nice concentration divided by quantum concentration type relationship. So the fraction of these molecules occupied by oxygen could be found by doing this: taking the number that are occupied divided by the total number, reworking so it looks like this, plugging in our equation for lambda, and we end up getting that, which can actually be rewritten like this. So this equation is actually something called the Langmuir absorption isotherm, basically talking about absorption of gases on the surface of solids. So this is pretty much all in terms of pressures and the temperatures. All right. Here's another question dealing with the Gibbs factor. Pause video, work on this stuff, and we'll go over in a second. All right. So based off of this, I can actually develop my grand sum. So here we have we have one particle that will end up giving us an energy of this. So what I can say here is that for one particle in the ground state, it has an energy equal to this. Then for the next one, I plug in 0 with its energy, then 2 in for the n, and then its energy, and then 1 with its energy. So cleaning all this up and moving things around, I end up getting this. So what I can do, because they want to find the condition for this lambda term, so I'm going to take the partial derivative of this with respect to lambda, and I'm getting this equation. So the number of molecules, remember we found it to be equal to either of these equations. Since we're dealing with terms of lambda, we're going to work like this. So from here we can actually plug in the numbers that we have. So we know what the partial of the grand partition function as a function of lambda is. We could plug in the grand sum in, and we get this. And they told us that it's going to be equal to unity, which is another way of just saying 1. So the average number is going to equal to 1. And then from here we can just solve for lambda. So cross multiply, move this over to on this side. We could start crossing out things, like for example, there's this lambda e to the whatever, and there's this term, so this and this can drop out. This pretty much can combine with this term, so moving this over to here, this actually gets rid of the lambda, well, one of these, and then we could just, yeah, clean this up a bit, move some things around. So we end up getting this. So we get lambda in terms of sigma and tau, just as they wanted us to do. All right, here's another question. Pause video, work on this up, and we'll go over in a second. All right, they want the probability, the ratio of the probabilities of the two states. So um, there's actually two ways of doing this. One way is to think of our setup for the probability and then just literally divide both of them. Or we can actually remember that the probability of two states, state one and state two, is the ratio of these Gibbs factors. The whole point of talking about the Gibbs factor was that they're proportional to each other. So that's what this is doing. It's just saying that this is the Gibbs factor of one state divided by the other state. I can actually do this for the unoccupied state. There are no particles, no energy. And then for the other one, one particle, ground energy. So I end up getting this. And then again, want to try to clean it up a bit, substitute some variables in. I would say for a homework question or like on a test question, I would specify exactly what type of variables and what terms I would want it solved in. But if we want to go back to basics so that we have things that we would normally know, things like temperature, pressure, and mass, we can actually plug in what NQ is into the equation so that we get rid of these lambda terms. And we would end up getting this complete mess of an equation. All right. Here's the next question. Pause video, work on itself, and we'll go over in a second. All right, so we just want to figure out what the grand partition function is. So we have two particles, and it says that it could be in any of these three states. So my grand partition function is going to look something like this. Two particles, and I could either have both of them with zero energy, one of them with an energy. So one with energy E, the other one with energy 0. This both with energy E. This is one with energy 3E and one with 0. This with 3E and E, and this one both with 3E. So you almost have to kind of come up with like that probability tree or combinations of everything you could have with two particles. Either 0, 0, 0E, 0, 3E, EE, E3E, and two 3Es. And that's where these numbers are coming from, is that combination of picking two energies from here where we can double up on any of them. So the grand partition function just looks like this. There's really nothing else that you can do with that. All right. And that was pretty much it. Again, the basics of this entire course lecture was all about this chemical potential equation, the concept of how we find the potential based off of the concentration of the molecules in the gas, what we call the internal chemical potential, and then also about how we can add in external potential energies in order to create or maintain a internal difference in the concentrations. And then we also talked about how incorporating this chemical potential concept into our partition function will end up giving us what we call the Gibbs factor and the grand partition sum. And we also talked about how we can clean up this equation to actually replace this with lambda. And then here are the questions for chapter 5. all dealing with this type of stuff. All right. If you have any questions, please let me know. Otherwise, I'll see you later. Bye.